Welcome to Differential Equations section 4.2. In this particular section, we're still looking at systems of differential equations. They have some initial conditions. The algebra part of this, to say it's difficult, is an understatement. You could call it a nightmare. It's very difficult to get the exact answers. So use all the tools at your disposal. Take your time. It's extremely easy to make a mistake. So on the question one is fairly straightforward. We have this particular system. You can see x prime and y prime both depend upon x and y. So, looking at this, I have x prime as that. So, if I differentiate it again, I get x prime minus 6 x prime equals y prime. All right, but what do I know about y prime? All right, so looking at that, I know y prime is this stuff, so fill that in. What do I know about y? Well, look back at this, and so x prime minus 6x is y. So what did we do again? We took our first equation, differentiated it again. Now I'm looking at the second equation, filling in for y prime, filling in what I know about y, and so this is going to give me a second order equation. So when you clean all this up, distribute here, move everything to one side, I've got minus 3x prime, a minus 6x prime, so a minus 9x prime. And I've got a 2 and an 18, which is 20. So, second order problem. I now conform the characteristic polynomial. All right, so got that. R squared minus 9r plus 20 equals 0. It's nice. I don't have to use the quadratic formula because it does factor into minus 5 and minus 4, giving me that R1 and R2 are 5 and 4. So x is C1 e to the 5x, C2 e to the 4x. So now I go back to what I knew about y. So y is, all right, so I'm going to need x, which I've got. I'm going to need to differentiate this. That's why you see a 5, C1 e to the 5x, and this 4, C2 e to the 4x, minus 6 times all that stuff. Okay, so first part here is x prime. Second part is from the x. All right, so clean all that up, collect like terms, and I get what I know now for y of t. All right, so I've got x of t, got y of t, but we've got some initial conditions. So x at 0 is 1. All right, so if I plug all this stuff in, and I am noticing as I'm saying this, that all of these x's here, and I'll fix this up in the notes, all of these should be t's. Yeah, because these are all functions of time. Get so used to making them with x's. So those are t's. All right, so we have all that, and so now plug in what we know from our initial conditions. I get a system of two equations and two unknowns, but I can add these up, so add them up, and I find that C1 is 2 and C2 is minus 1. And so when I look at my solutions with t's in there, it's going to ask me, based upon this, what does the field look like? So if you remember back in the video for 4.1, I plugged this into a system online and I was able to generate a direction field. I picked our starting off position that was sitting here, and I'm looking at the trajectory of that particular solution curve, and I'm looking to see it does match in MyLab Math number A, and so you can see that from the picture. Now, I also reworked the problem showing you how to use the D operator method, our differential operator. What does that mean? So, what you do is you bring everything to one side on the first one. I then know that this is so I'm dealing with x. D is the derivative. So that's the derivative of x minus 6 times x minus y is 0. And now do the same thing for the y equation. So looking at that, I've got, and I put it in order of x's and y's. So here's my x stuff. Here's my differential operator working on the y part. All right, and so you then form this determinant, which I call L, and L, this 2 by 2 determinant, will be 0. So it's the downward diagonal minus the product of the upper diagonal. It's minus a minus, so it's plus 2. And so you see we get this differential operator equation, and that should look familiar because it looks like the characteristic polynomial we had. And it does factor into 4 and 5. And so that tells me my roots are 4 and 5. So x of t would look like this. Y of t is going to have different coefficients, but we can actually work on this and see how it depends upon the coefficients for x. All right, so what did I do? So I took my equation here. So here was my system. Let's come up a little higher. So here's the system. So take x prime and put that in here. That equals 6 times the x part plus the y part. And so if you start matching up stuff, the e to the 4t part is here. E to the 4t is there. E to the 4t is there. So if I move this over, I've got 4 minus 6 is a minus 2. And from the b part, I'm going to leave that there. So I don't care about this piece because that's the same. And I can divide by it. It's not 0. And so I get b1 is minus 2a1. If I do the same thing for the e to the 5t stuff, that's in 3 places, I get this relationship. Again, don't care about e to the 5t, but I see that b2 is minus a2. All right, so now if I use what I know about all this stuff, plug in my initial conditions, I get this system. Notice if I just plugged it in using my first answer, nothing was going to cancel because these don't match. But when you put in the determination how the b's depend on the a's, it's now all related to A1, A2, and you can simply add these. The A2's go away. You get A1 is minus 1, A2 is 2. Now what's B1? B1 is minus 2 times A1, and since A2 is 2, then B2 is minus 2, and we finally get our solution to the problem. All right, not too bad. Algebra still somewhat terrible. In question 2, we have a system of differential equations. We now have 3 equations, and things get messier. So I still went with the differential operator method. So what did I do? I moved everything to the left, cleaned it up, got d minus 3x, got a minus 4y plus z. I repeated that for number 2 here. Got everything to one side. Don't have any y's. All I have is this single y prime. So just the differential operator. And then here with z's, did the same thing. Move everything left. All right, I've got, let's see, this part up here. I left off a 7z. All right, so left off the poor 7z. So that's there. So this is going to give me d minus 7. And so if I plug all of that into my determinant, which is now a 3 by 3 determinant, it looks like this. Now I'm going to expand this determinant by row 1. So I'll put that here. Expand by row 1. All right, so if I do that, it's this times this subdeterminant. If you remember how the positions go, there are signs. So it goes plus, minus, plus, minus, plus, minus, plus, minus, plus. And since I'm expanding by this top row, that's where that minus came from. So the minus is from the position. There's a minus 4 there. It's subdeterminant. Got the 1. It's a plus. It's in that position. All right, so basically grind through that, which takes a bit of time, and then collect up like terms. All right, so it's looking better. So again, there's a lot of algebra here, easy to lose something. All right, so still looking good. The problem is here, we need to multiply this thing out so I can get the 9 into the game. All right, so if I did that, turns out I do get a minus 9 out of it, which cancels that. And so I get a third order equation. Is factorable. Takes a little time, but fairly easy. And I get answers of 0, 6, and 4. All right, so those are my roots. So e to the 0 is just a constant. I'm going to get an e to the 6t and an e to the 4t. So the good news is we now know what x, y, and z must look like. That's the good news. The bad news is I now need to understand how B1, B2, B3, C1, C2, C3, how they all depend on the A's. That takes time. So I found x prime, and x prime is just differentiating that. Got that. And what's it equal to? Well, 3 times the x, 4 times the y, minus the z. That's what all this stuff is. So now we get the fun task of matching everything up. All right, so I moved all of this stuff to the right, distributed all this stuff, and so now I'm looking at what goes together. All right, well, all the stuff that is a constant is right there. All the stuff in front of a e to the 6t is here. All the stuff in front of the e to the 4t is there. Simplifying that, collecting that up, we get that relationship. Now, that's not quite usable. I can't just set all this together as a matrix and solve, because this one involves the ones, this one the twos, this one the threes. So that means I must repeat this whole process for y prime. Fill in everything I know about y prime and collect up everything and then see what matches. Now, looking at the left here, there are no lone constants. That says that a1 plus c1 must be 0 because there's none on the left. And so that says minus a1 is c1. And we had earlier that relationship. And so if I plug in what I know about C1, I can solve for B1. So what that means is I now know what all the ones look like. I know that C1 is minus A1. I know B1 is also minus A1, and A1 is A1. So now that takes care of the ones. So now I grab all the stuff involving the e to the 6t, compare. Grab all the stuff with the e to the 4t and compare. And then I get equations for them. So remember, earlier I've got 2 equations up here for the 2's and the 3's. I've got another 2 equations here for the 2's and the 3's. And now my third set. So here's z prime. Plug everything in. Start matching things up. And when I did, I noticed that I'm looking at the constants, and all of that must add up to be 0. So just to check that I got everything right before with the ones, I plugged in what I knew about that stuff. And this should be C1. I'll get this all fixed in the notes. Easy to make typing errors here. All right, so then I plugged all that stuff in and I checked, and yes, that did give me a 0. And so now I grabbed all the stuff with the e to the 6t's, e to the 4t's. Simplified that and I got my last two equations. So I put it all together. So here's all the 2 stuff, the 2 variables. Here's all the 3 stuff. So I've got 2 systems of 3 equations and 3 unknowns. And I said, okay, I'm just going to let Wolfram Alpha solve this for me. And I used row reduce. And so you just grab off the coefficients of your matrix for each piece. So that's what you see here. So this shows you the format, how to do the row reduction. And then it will give me the answers. But I need to interpret them. So let's see. What does this say? This was for the 2's. The last row is all zeros, so that says C2 is T. If I look at this row, I get B2, move this to the right, which is 0, 1/7 T. And from the top row, I get A2 is minus 1/7 T. So, what do I want T to be? Because I want A2 to be A2. So, I let T be minus 7A2. And that's going to give me what B2 and C2 are. Alright, hopefully that's clear. I did the same row reduction on the other one. Game is played the same. Bottom row is all 3's. So we have a linearly dependent solution. I get C3 is T. Moving again, B3 is 1/13 T. And A3 is a minus 9/13 T. How do I pick T again? Well, I want everything to depend on the A's. So I let T be minus 13/9 A3 because when I plug in that T, I want A3 to be A3. So I then see what C3 is and what B3 is. And so I can finally conclude what X, Y, and Z are. We already knew they were the constant e to the 6t, e to the 4t. But what we were missing was how this other solutions depend upon the coefficients in X. Now, I could have solved the whole differential equation using alpha. I could just say, solve this system. And it did it, so you can see how it writes it. But I can't say the solution is very meaningful looking. I mean, I could go in here and start collecting off all the coefficients. It does show me how things depend because they're all in terms of C1, C2, and C3. But I can't say the solution is very meaningful. All right, again, use lots of tools, easy to make all kinds of mistakes, either in typing or calculating. All right, in question 3. Question 3 is I've got 2 tanks. I've got some fresh water coming in here, 20 gallons per minute. Got a 100-gallon tank here, a 200-gallon tank here. Is leaking out here of 30 gallons of tank 1 into tank 2. Tank 2 is also sending back 10 gallons into tank 1. Tank 2 started off with 200 gallons. It's leaking at 20 gallons per minute. So they're also telling me some information about the initial concentrations. So at time 0, tank 2 has 0.25 pounds per gallon. My X and Y give me pounds of salt, not gallons. And so if I plug in, I can find that Y at time 0, there was 50 pounds of salt in this 200 gallons. And at time 0 in tank 1, its concentration was also that same 1, but it was in 100 gallons. So X at time 0 is 25 gallons, 25 pounds. All right, so I take my differential equation system here, and the answer is going to involve decimals. And they say don't round this until the very end, and then in the end round it to the nearest hundredth. This is extremely difficult. So if when you work your problem, you get something that's almost your answer, but the decimals are just off and you just can't fix it, let me know and I'll give you credit for the problem, because it's extremely difficult to get this thing accurate enough for MyLab math. All right, so we went the differential operator method, brought everything to one side on both of them, and I got our particular system. I formed L, which must be 0. It's easy, just grab off the coefficients for each of your pieces. And the product, this product minus the upper product, must be 0. All right, so I get there. And I get this particular characteristic equation. I did reduce it. Okay, so I could divide it by 2. I saw I could divide it by 2 again. And so I get a quadratic equation, not factorable. So I do need to use the quadratic formula. Again, I used a tool because I didn't want to take time to mess with it. And so I could put it here nicely in our problem. So here's what it is. And so R1 and R2 look like these, and here are the decimal numbers. And we've got it more than we need for the 100th place, but leave as many as you can see. So the good news is we're essentially done. I now know what x of t looks like. To figure out what y of t will look like, I plug all this stuff in. All right, now I'm starting to match coefficients. All right, because I've got that the y answer, and let's just put the y answer here. If I put the y answer here, my y of t would look like B1 ER1T plus B2 ER2T. But again, I need to know how the b's depend upon the coefficients in x. So I plug this stuff in, plugged in what I know about y, and then I'm going to start matching up coefficients. All right, so I did all that, but when I do that, I get B1 looks like this, but it also depends upon R1. B2, I've got a relationship for it, but it depends upon R2. So here was my R1 and R2. So I do know how B1 depends upon C1, and I know how B2 depends upon C2. But the problem is I don't really want to carry all of this stuff as we go forward. So I plugged in what I knew about R1, calculated all this, and then I kept as many decimal places as I could to figure out B1 and B2. So again, just plug in as many decimals as possible, because in the end you need to round it to the nearest hundredths place. So once I did that, I then plugged in what I know about x0 being 25 and y0 being 50. And that gave me my system of two equations and two unknowns. And I could again start solving for C1 and C2. All right, so here's what I had. And to keep things as accurate as possible, I used the tool to try to solve that. And so I got C1 and C2. I plugged those in and I rounded them to the hundredths place to get x and y. And again, you could have solved the whole system using Wolfram Alpha. But again, very difficult to get the decimals to match up exactly. So again, if you have difficulty but are close but just don't quite get there, don't pull your hair out. Let me know and I'll give you credit for the problem. If you use alpha to solve it, it will, and it shows it to you here what the answer would look like. I also put the code into Mathematica itself, and you can see it puts in your R1 and R2 in the most accurate method possible. But you would have to sort through and actually, figure out what's going on. But this would be the most accurate because it keeps R1 and R2 with all the radicals and the solution from our quadratic equation.